All right, it's my pleasure to introduce this week's speaker, Giuseppe Barbaro from Aarhus University, who will speak to us today about toric generalized Kähler-Ricci solitons. So please, Giuseppe.
Yeah, so thank you for the kind invitation. So today I will talk about joint work with Jeffrey, but also like Vesti and Yuri. This is about generalized Kähler-Ricci soliton. So let's start putting everyone on the same page on what is generalized Kähler metric. So let's say we have a Riemannian manifold and we have two compatible complex structure. Then I will denote by omega I and omega j the two Kähler forms, and dci and dcj, these are the two like, twisted differentials. Then generalized Kähler metric is a metric which is so yeah, I mean G is Hermitian between for both I and J, and we need these torsion forms, these torsion tree forms, to be one the opposite of the other, and both to be closed. Now, of course, like a Kähler metric will trivially be a generalized Kähler. You can just take GI Kähler and J, like you take like minus I, and then it would be a generalized Kähler. But in general, generalized Kähler metric are not Kähler. They are more likely like is like having twice a pluriclose metric. So like this condition is precisely like the pluriclose condition for the Hermitian structure GI. Okay, then what one usually do when is dealing with pluriclose metric is working with the Bismuth connection. So we do it also here. And Bismuth connection is the only Hermitian connection, so it preserves both the metric and the complex structure, which has skew symmetric torsion. And the torsion is precisely this tree form. So we have the Bismuth connection for the I structure and the Bismuth connection for the J structure. And we will call in the future like Ri and Rj are the curvature of this bismuth, and rho I and rho j are the Bismuth-Ricci form. Okay. So as I said, we were gonna talk about soliton. So just like very quickly, why should one be interested in solitons? Well, it's because these are limits, like historically in the work of Hamilton and Perumal, like they arise as limit of the Ricci flow, and they are models for the singularities. So let me just recall the equation. This generalize the Einstein equation by adding a term which is saying that the metric is changing in a self-similar way. So here you have a Riemannian manifold, and a steady Ricci soliton is something that satisfies this equation. So as I said, this flow limit, like if you run the Ricci flow here, like you see that is changing the metric in a self-similar way. And another comment, in general, on the right-hand side, you're gonna have like some multiple of the metric. Here for today, we only care about steady Ricci solitons. So we have 0 here. And this vector field will be called the soliton vector field. And then an interesting case is when this vector field is the gradient of a function. So in this case, the equation will transform in this way. So we have Ricci plus like a nation of this function equals 0. And we will call this now a gradient steady Ricci soliton, and F is the soliton potential. So this is from the Riemannian point of view. Then if you add a complex structure and request the metric to be Kähler, then this will be the equation of a steady Kähler-Ricci soliton, and this is the equation of a gradient steady Kähler-Ricci soliton. What we're gonna study today is a generalization of this equation that allows for some torsion in our geometry. And these are generalized Ricci solitons as introduced by Mario Garcia Fernandez and Jeffrey. So the equation is as before. We have now Ricci plus this Hessian of f equals 0. But we're not considered the Levi-Civita connection, but like a connection which has a torsion. And the torsion is this free form. So why is this equation interesting? Well, this arises from string theory in the physics context, but from a more like mathematical point of view, again, these are like flow limits of the generalized Ricci flow. So like this might be your motivation for being interested in them. And now, like, see that here, like everything is Riemannian, and we just like allow from some torsion in our geometry. And a particular case of interest is when this torsion is related with our structure. So in particular, we can put a complex structure here and ask this to be the torsion of this Hermitian structure. And this is precisely the case we are interested in. So let's say we have a generalized scalar manifold as before. Then we will say that we have a generalized Kähler-Ricci soliton if both this triple and this triple are generalized Ricci solitons. Okay, so we just asked for a generalized Ricci soliton where the torsion has some compatibility with the Hermitian structure. Okay, now very interesting. These solitons, they are like we have a characterization of them, and this is due to Jeffrey and Yuri. So they proved that if you have your generalized Kähler manifold and like the soliton potential, then like having a generalized Kähler-Ricci soliton is equivalent to the fact that like you have these two vector fields. Here, theta is the Lie form of the Hermitian structure with respect to J, and the Lie form with the Hermitian structure with respect to I. So you cook up these two vector fields, and these two, they have to be Killing, holomorphic, and satisfy these equations. And this completely characterized being a generalized Kähler-Ricci soliton. Now, very interesting, like we have, I mean, this gives some symmetry of all your generalized Kähler structure. So what we could prove is that like if you actually have a generalized Kähler-Ricci soliton, then the vector field xi is not just holomorphic and killing, but it also preserves the other complex structure. And the same for xj. So both of them, they preserve all the structure. They are also commuting. And there are also like some other properties, but these are the ones that we need. So they preserve all the structure and are commuting. So like you see that like we have this abelian symmetry. So we are going in the direction of toric geometry. Like in the title, like, as I said, we're gonna study generalized Kähler-Ricci soliton with some toric arguments. So like we're going in this direction. We have our abelian symmetries. But now, of course, like you might say, like you might be interested in understanding, like if these are real symmetries and like how many they are in some sense. So this motivates the definition of rank, which is the sum of the dimension of the span of these two vector fields. I mean, if these two vector fields are vanishing, means then we don't have like this symmetry, or they can be equal. Um, so these are the general cases, which actually are already classified. So in particular, if the rank is 0, so it means that the two vector fields are vanishing, then we have an hyperkähler structure. So this is a result from another work with Besti, Lee, and Jeffrey. So in this case, what do we prove? Now, suppose you have a steady pluriclose soliton, which is like half of a generalized Kähler-Ricci soliton, right? So you have your emission structure, this is the torsion, and then you just have like this triple to be a generalized Ricci soliton. Then the vector field is vanishing if and only if the metric is scalar. Okay. So a steady pluriclose soliton is as I said, is half of a generalized Kähler-Ricci soliton. So here, if the rank is 0, means xi and xj are both 0, so the two structure are both scalar. So rank 0 case is easy. What can we say about the case of rank 1? So we actually have like at least one symmetry. Well, in low dimension, in dimension 4, these were classified again by Jeffrey and Yuri using the Gibbon-Hawking ansatz. This is something that we're gonna see in a few slides because we're also gonna need it. But anyway, in dimension 4, the rank 1 case is clear, is classified. So let's move to the last remaining one, which is the rank 2 case. This is what we're gonna be interested in today. And so you see, we have like 4 dimension with 2 symmetries. So like these abelian symmetries are half of the dimension of the space. So like we're really going in the direction of doing toric geometry. So what else we need? For this, we need symplectic structure. Okay, so let's put a symplectic structure in the picture. We will say that like a generalized scalar manifold is of symplectic type if one of these two forms is defined globally. Okay, so here, I mean, this two form, like in general, might be not defined because like this might be not invertible, but when it is, these are symplectic forms. And yeah, and we call it symplectic type if these are globally defined. Now, the point is that in dimension 4, asking for symplectic type is not really restrictive. In fact, like we only have 2 cases in dimension 4. Either the manifold is of symplectic type on an open dense subset, or it has a split tangent bundle. And the case where it has split tangent bundle, like the 4-dimensional manifold with split tangent bundle, these were classified by Besti and Gualtieri. So in dimension 4, up to like studying our problem on an open dense subset is not restrictive to ask for symplectic type. Okay, so this is what we're gonna do. So we're gonna think about like studying this problem on this open subset. So let's characterize it a little bit better. So whenever we have our generalized Kähler structure, we get this Poisson tensor. We just take like the commutator of the 2 complex structures and like we do the inverse with G. And we call the generalized Kähler structure commuting if the 2 structures are commuting, or we call it non-degenerate if these 2 are not commuting, and then it means that sigma is not degenerate. And if it is not degenerate, like it can be inverted, of course. Now the point is that four-dimensional is like it's special, and the Poisson tensor is non-degenerate apart from this locus here. So the only points where this Poisson tensor might be degenerate is, is the locus where I is equal to plus or minus j. And the point is that this has complex dimension 1. So the complement of this is an open dense subset in our manifold where sigma is non-degenerate. And like the inverse of sigma gives a symplectic structure omega, and we can cook up other two symplectic structure omega I and omega j. So we have these three symplectic forms. Okay, so now let me talk about the Gibbon-Hawking ansatz. So this was used originally by Gibbon and Hawkins to describe hyperkähler four manifolds with three Hamiltonian, like with an S1 action, which is Hamiltonian with respect to all the three symplectic structure. So here I didn't give you like the definition of hyperkähler, but like maybe you know it. So this is a Riemannian metric which is Kähler with respect to three different complex structure. And so like you have these three Kähler structure which are precisely like the three symplectic forms that you're looking at. And you're supposing to have an S1 action which is Hamiltonian with respect to all the three of them. And they use these ansatz to describe these metrics. So now in the generalized Kähler case, you can do the same using the three symplectic forms that we saw before. So like you're supposing, at least locally, to have an S1 action, which is Hamiltonian with respect to the three of them. So like you look at like your moment map with respect to this action, it will go somewhere in R3. And now the point is that like you look at them locally as an S1 bundle over the image of the moment map. And the point is that like you can characterize the metric as a bundle-like metric. So let's call like here omega is detecting like the length of the vector field X, and then the metric will be like bundle-like. So it will be something here accounting for the vertical direction on the fiber S1 and an horizontal one, H. And the point is that like this eta, looking at the S1 direction, is a principal connection, and its curvature depends on omega, and omega satisfies analytic PDE. Very similar to the original Gibbon-Hawking ansatz. Okay, and the point, due to Jeffrey and Yuri, is that any non-degenerate generalized Kähler manifold, which has like this three Hamiltonian action, is like it can be described using these ansatz. And as I said before, like now that they had these characterizations of this metric, they could use it to characterize and like to classify the rank 1 case. Okay. So this was useful for the rank 1. It turns out it's very useful also for the rank 2, of course. So what is the difference? The difference is that now we will do this Gibbon-Hawking ansatz. We will just do it twice. So suppose you have your non-degenerate rank 2 generalized Kähler-Ricci soliton, and we have the two vector fields that are preserving all the structure. So as I said, we can do these Gibbon-Hawking ansatz twice. Uh, with respect to omega, omega I, and omega j, and we do it twice, and we cook up all these moment coordinates. Now, an important thing, I mean, this is a little bit technical, but the point is that like this moment coordinate here, mu1, this will not really count because somehow, if you look at the description with respect to this vector field xi, these coordinates will be on the torus on the S1 of the other vector field of xj and vice versa. So since in the end we're not like the image of the moment map that we care about is not going to R3, but we're gonna go down on R2, like we have to remove like 2 dimensions. And what I mean is that like only this mu2 and mu3 will be the important ones because this one will be accounting for the direction on the other torus. But this will be probably a little bit clearer in the next slide. So anyway, we don't consider these two. And the point is that these mu2 and mu3, they give moment map for the symplectic forms that we saw before, F plus and F minus. And these are the symplectic forms that we're going to use. So it turns out that if you look at these two symplectic forms, the vector fields, like they vanish on xi and xj. And this is, I mean, this is a condition that you need. Like you need the torus to be Lagrangian for your symplectic form. So this is something that we needed for applying toric methods. Okay, so yeah, we did this Gibbon-Hawking ansatz twice. So this means that we can split the tangent bundle in two different ways. Like one way with respect to xi and one way respect to xj. And here, like the horizontal component, it will be spanned by I of xi, j, xi, and k of xi, where k is just like the commutator of the two of them. So, and yeah, we can do this twice. So like you might ask, what is xi when I try to read it here in the xj decomposition, and vice versa, what is xj when I try to read it in the xi decomposition? Well, it turns out that like xj is a multiple of xi and k of xi. And this is like what I was trying to say before, that like when you go down on your moment map in R2, the two directions that counts are the one generated by IXI and J of XI. Because this other one will be on itself on the torus, will be related with XJ. Anyway, a direct and important corollary of this description of xi and xj, one in terms of the other, is that if you look at at your torus, then I of your torus is equal to j of the torus. This condition is very important. It's probably not clear why in this slide, but it will be in the next one. But let's keep it in mind. This holds for four-dimensional rank 2 case. Okay, so up to now, what we did was somehow proving that four-dimensional rank 2 we can do toric geometry. Like we have these symmetries, they're preserving everything. They are abelian, half of the dimension of the space, and we have our symplectic form. This torus is Lagrangian for the symplectic form, and we also have like this yes.
Can I ask you, can you explain why, probably I'm missing something, why IT is equal to JT? Probably I'm missing something. And you told me
So
on the slide, but I don't see this immediately.
So it's because okay, if you do I of this, so here you get I of xi. Okay, is in the way uh, okay, maybe it's not really immediate. Like the point is that what happened when you do I k, you get something like identity and then the other complex structure.
Yeah, you should get maybe J. I don't know. Okay.
Yeah, I mean, it's
Okay,
probably
but
not really
okay.
immediate just looking at this formula, but it is easy when you write it down.
Okay, thank you.
Okay. Yeah, I'm sorry, like I cannot like give you like straight from here, but it's just like a couple of lines. Okay, so anyway, I was saying, um, so yeah, in dimension 4 rank 2 we can do this toric geometry, but so let's do it in general. Let's consider in general that we have generalized Kerr-Ricci soliton on um, in a toric setting. So let me define a locally toric manifold as like we have a symplectic manifold, two n-dimensional manifold, and then we have like a space, like we have n symmetries, so half of the dimension of the space in abelian symmetries, and we need this one to like to span like we need this distribution to span a maximal subspace, so like rank n at any point, and we need the symplectic structure to vanish on them. So these are the I mean these are the conditions for doing like toric geometry locally. And I mean, as we saw, that these are already like we checked that this is happening for the rank two in dimension 4. So now, once you have this, like as usual, you can take the contraction of your symplectic form, and this gives you like a moment coordinates, and then you also have like the angular coordinates, and the symplectic forms reads in this easy way. And having a Keller metric which is compatible with this symplectic structure it is just given in this way. So you just need a matrix G, which is so this has to be symmetric and positive definite, and then you call H its inverse, and then you construct your complex structure in this way and like metric in this easy way. And this would be Keller. This gives you a locally toric Keller structure. And notice here, yeah, the G also has to satisfy this Hessian condition. Here, whatever is coming after the comma is derivation. So in particular, as I said, so this is symmetric and positive definite with this Hessian condition. So in general, what you do is instead of looking at G, like you look at the Hessian of some function. So this is something that like you can do always locally. Okay, so now the point is that we have a canonical way of constructing a generalized scalar metric starting from a locally toric Keller metric. And this is due to Boulanger. So what is the point? The point is that like you do this A deformation of your Keller structure. So what is A deformation? You just like you become skew-symmetric matrix A. You define your new matrix here as the G of the Keller one plus A, and you take the inverse, and now you cook up like the Riemannian metric as before, and the two complex structure I and J, they differ by like in one of them you take the transpose of psi. And this is generalized scalar. And the point is that like the generalized scalar locally toric are classified. I mean that they're characterized, at least the one that come from an A deformation in this way, and are precisely the one for which this condition that we saw before on the torus is holding. So if you have your symplectic type locally toric generalized Keller structure, then this is coming from a Keller one using this A-type transformation if and only if you have this condition. And we saw that this condition is holding in the rank 2 case. So in the rank 2 case for dimension, we know already that that structure is coming from a Keller one. Okay, so now I can state our main theorem. So suppose you have symplectic type locally toric generalized Keller Ricci soliton. Now we need, like we asking the two vector fields given by the soliton to be among the abelian symmetries that we are considering. And we ask for this condition, the A-type deformation condition. Then what we know is that this generalized Keller structure will be A-type deformation of a Keller one. This we know already. And what we're adding on top of this is that the Keller one is actually itself a Ricci soliton. So it's a gradient steady Keller Ricci soliton. And the soliton vector field of the Keller structure is just the sum of the soliton vector fields of the generalized Keller structure. And this works also in the other way. So if you start from a locally toric Keller Ricci soliton, and you want again the soliton vector field to be part of the symmetries that you're considering, then once you take any skew-symmetric matrix, you do your A-type deformation, you will get a generalized Keller structure, which is a generalized Keller Ricci soliton. Okay. And like as we saw in the beginning, we already proved again that like our motivational case, the fourth dimension, is satisfying all these conditions. Okay, so let me like very briefly sketch the proof of this. Okay, yeah, before sketching the proof, I need to like recall what is gonna be locally toric Keller-Ricci soliton. So the equation is the Keller-Ricci soliton equation that we saw before. The only thing is that like your soliton potential is some t invariant function. And so like you can write it in like linear way in the moment coordinates. And then these solitons, they are completely characterized by satisfying a Monge-Ampere equation. So the point is that like B you have this constant B, which is given by the soliton potential. And then there exists another constant C such that this twisted Mojan-Pair equation is holding. Okay, so we have here in this slide a characterization of Kerr-Ritchie soliton, and we had a characterization of generalized Kerr-Ritchie soliton. So we're going to use the two of them and show that we can go from one to the other with A-type deformation. Okay, so let's start with a Keller-Ritchie soliton, and we have to cook up a generalized Keller one. So as the statement is saying, like you have to take any skew symmetric matrix, you perform your deformation, and now like you know what is I and J. These are given by the formula I gave you before. So you directly compute the Lie forms, you compute the Bismuth-Ritchie forms, and so on. And then what you do is that like once you compute all of them, you check that these vector fields xi and xj, they satisfy the characterization of generalized Kerr-Ritchie soliton. So what I mean here, like you define xj in this way, b plus ac, and this is b minus ac. So by definition, like b is something in the torus, C is in the dual of the torus, so AC is in the torus. So like these vector fields, you already know they're Killing holomorphic. What you have to check is that when you do the Lie derivatives of omega with respect to them, you get the Bismuth-Ritchie. This was the characterization of generalized Kerr-Ritchie soliton. I mean, half of it. Once you check that, then you prove that they are actually equal to the vector fields in the characterization of generalized Kerr-Ritchie solitons for a given, for like this given potential here. Okay. On the other way around, if you start from a generalized Kerr-Ritchie soliton, then what you do like is like you have to deduce this formula. The way of deducing this is because so the DDC of this thing here, DDC of log that Hessian of U is gonna be the Bismuth-Ritchie form, and the DDC of this is the Lie derivative in the direction xi or xj of omega. So by the characterization of generalized Kerr-Ritchie soliton, DDC of this thing is 0. So this function here is pluriharmonic. And the point is that like you can characterize pluriharmonic functions, and like they're just linear in these coordinates here. Okay, so once you have this, you compute, like you check that these equations hold. And now the point is, see here, like we proved this one with fj for fj this, and fi for a particular fi, but you know already that here you could put just half in both of them, and you would get the same vector field. So this means that you can, like that these two, they have to differ by a constant. And the determinant of Hessian plus A and Hessian minus A is the same. So the fact that they have to differ for a constant, it means that this Ci and Cj, they have to be equal. They have to be equal, and they give you your constant C. What else are we missing for the Mojan-Pair equation? We need the constant B, but that's easier. Like if you look at the way we argued here, like the way of obtaining B is just by summing these two. So I take xi plus xj, and I call this B. Okay, and now like these are two equations, one for I and one for j. If I sum them here, I get xi plus xj, which is b. This stays the log determinant of the Hessian. This is c, is the same for both of them. Here, this one is erasing because one time is plus one, the other one is minus. So we only have this. And this is precisely the Mogent-Pair equation of the Keller-Ritchie soliton. Okay. So I repeated like the same slide here just to sum up. So the point is that using this A-type deformation, we can go, I mean, we knew already that this would go from locally toric Keller to locally toric generalized Keller, but the point is that it sends solitons to solitons. Okay, now just remember, like in theory, like everything here was happening on an open dense subset. So now the question is, will this structure like extend to all the manifold? So let's clarify this point. So we know that if if we have our symplectic structure, like locally toric structure, and let's say that we have it on the whole manifold M, and then on an open dense subset, we have our locally toric Keller and locally toric generalized Keller, which are linked by the deformation. Then one of them extend to the whole manifold if and only if the other one does. Okay. So let's put it in another way, like we have this Keller and generalized Keller linked by this A deformation on our open dense subset. And the fact of like we know that we can deform one, we can extend one if and only if we can extend the other. But for having this condition, we really need the symplectic structure to be defined on all the manifold. And this is clear, like why this condition has to be there is clear in like an easy example. So like let's look at the op surface. So like this is my picture of an op surface. So like this is C2 minus the origin, and yeah, like we're gluing these spheres. Okay, so in here, like on the op surface, we have a generalized Keller structure. But the way it is defined, like we have I and J, and the point is that we have one elliptic curve, let's say like the blue one, where I is equal to minus J, and we have another elliptic curve where I is equal to J, the red one. So these two elliptic curves, they are our degeneracy locus. So if I remove these two outside, the structure is non-degenerate, and I can do like everything we applied before. Like actually, let's say you only remove the like the red elliptic curve, so you have a symplectic structure which is precisely F minus, because like you're only avoiding the point where I is equal to J. So I minus J will be invertible, and we have F minus all outside the red part, and we have our moment map, and this would be half space. So, and if you look at this picture here, like the blue line is the elliptic curve blue, and the red elliptic curve in this moment map picture is being pushed to the infinity. And you can do the same with the other one. Okay, but like crucial point here is that like we have a generalized Keller structure which is global, but like we know, of course, we don't have a Keller structure which is global in the op surface. And this is because this symplectic structure, it does not extend to the whole manifold. Okay, so we've seen that the chance of extending the generalized scalar structure is precisely equal to extending the Keller one. So let's put ourselves in a setting where we understand very good how and when we can extend the Keller structure. And this is in the like when we have a Delsand polytope and Delsand condition. So let me define this. So now we take we want our symmetry to be actually like a compact torus T. And we will have like this moment map, and we say that we are satisfying the Delsand conditions if the moment map is proper and the polytope is a convex simple polytope. So convex closed convex simple polytope, it means that this is the intersection of a finite number of hyperplanes. And like for each hyperplanes is detected by a linear function L. So now notice here that we are in the non-compact case. So like the compact case would be when the polytope is bounded. Here, like Ham is not compact, and this polytope will be unbounded. But the point is that all the Delsand arguments they are local in nature, so like they can be extended to this case by substituting the compact property with the properness of the moment map. So so we know that the Keller structure can be extended to the whole manifold if it satisfies the Abreu-Guillermin condition. So for what we saw before, this means that the generalized scalar structure can be extended if the potential U satisfies the Abreu-Guillermin conditions. And these are precisely like the one I put it here. So like you need the difference of this metric to be, or this potential to be smooth, and also this thing to be smooth. And here UC is like the standard Keller potential. Okay. Okay, so at least in this case of Delsand polytope, we know when our generalized Keller structure can be extended to the whole manifold. And now the question is it gonna be a complete metric? So let's check this. So the point is, like as before, like boiling down in simple terms, we know that the generalized Keller structure is complete if and only if the Keller one is complete. So here, like you are in this, with this Delsand condition, you have the you have these two structures which are linked by A-type deformation on the interior of the manifold, like corresponding to the interior of the polytope. And you already checked that like you can extend both, and then the point is that one is complete if and only if the other one is complete. And why is this true? So this is because checking the completeness, it means that like you're checking like you're studying the you're studying like you're checking the properness of the distant function. And here like you have these compactors acting by isometries, so like you can just like remove it and study the properness of this distant function on the quotient. And the quotient M over these compactors is gonna be like a manifold with let's say a manifold with corner, which is the polytope. And now on the polytope, like you're just looking at the horizontal part of these metrics, And if you remember how is the A-type deformation, it is saying that like the horizontal part of this metric is the same. Because like here, the horizontal part is the Hessian of U, and here it is the symmetric part of Hessian plus A, but A is Q-symmetric, so you're just removing it. So the horizontal part is the same. And yeah, of course, it's a little bit more involved. You have to be careful when approaching the boundary. But yeah, the point is that all the time you go on a face of the polytope, this same argument will apply again and again. Okay. So we did all this, as I said at the beginning, at least in this talk, like the initial motivation was the rank 2 case. But actually, like this has inside, like you can apply these statements also to the rank 1 case. So like you can think about having a toric, like a locally toric generalized Kerr-Ricci soliton, which is rank 1. And it turns out that if you look at that, so like for example, what it means that like you have these abelian symmetries, and only one will be given by the soliton vector field. But then like you also have all the others, and you can apply all this machinery. And if you look at the equivalence between generalized Keller-Ricci soliton and Keller-Ricci soliton in this context, it turns out that the rank of the generalized Keller-Ricci soliton is at most 1 if and only if its counterpart is Keller-Ricci flat. Okay, so at least one direction of this is easy to understand why. If you have Keller-Ricci flat, this means that like in your Monge-Ampere equation for the Keller-Ricci soliton, it means that the constant B is 0. You don't have it because there is no soliton potential. And if you remember how we define xi and xj starting from Keller-Ricci soliton, they were B plus AC and B minus AC. But if B is 0, it means that these two vector fields are just one minus the other. So this is why if you start from a Keller-Ricci flat and you do this construction, you end up to a generalized Keller-Ricci soliton, which is at most rank 1. So to put also this one in boxes, we have seen that using A-type deformation, you go from Keller-Ricci solitons to generalized Keller-Ricci solitons. And then if you start from a Ricci flat, then you go into something which is rank 0 or rank 1. Okay. So I think this is all I wanted to say. Thank you for the attention.
Thanks, Giuseppe. Are there any more questions?
Maybe I have a silly question. Can you hear me?
Yeah, go ahead.
Oh, okay. So for all of these results, it was for the manifold was a half-dimensional torus. Like it had a half-dimensional torus for everything.
Mhm.
Is there like a physical reason for this, or like yeah, is there a reason that the torus is always half-dimensional?
I mean, the torus is not always half. I mean, having a torus which is half of the dimension of the manifold is like the condition that you need for doing toric geometry. Like toric manifolds, they have a symmetry which is like half of the manifold in dimension.
Okay.
But then, like Of course, like you cannot always guarantee that this happen. What we checked is that in the rank 2 case, for dimension rank 2 case, this is actually happening. But like for example, if it was rank 1, then you would only have one symmetry and like you would be missing the other one.
Okay. Okay, thank you.
Thank you for the question.
Any others? Okay. Well, yeah, if not, I guess.
There is
Oh,
some
sorry. Or yeah, whoever, yeah, Josh.
Yeah, I was wondering, I mean, so these A-type deformations, right? They're deformations by two forms. Do you know if these match up at all with like the deformations that Jeff and Matt Gibson, I want to say, discussed?
I could answer that easily.
yeah.
Uh, it's kind of different. Like in this paper with Gibson, we're basically working out what is kind of the meaning of a generalized Kähler class, at least in some sense, at least in the sense of kind of infinitesimal deformations by a generalized Kähler potential. That's kind of what we're doing there. Whereas here, I mean, I would say it's still not exactly 100% clear what the definition of a generalized Kähler class is, but morally speaking, you're deforming the class when you do this deformation. And what it is, it's just it's pretty much a very concrete instance of this line of ideas that goes basically way back to Hitchin at the very beginning of generalized Kähler geometry, where some of the first examples they constructed were doing what where they sort of like deform a Kähler metric by a Poisson tensor. That's kind of the way they first. So you're sort of turning on the Poisson geometry, and at least like to first order, these A-type deformations are basically these Hitchin deformations. Mhm. So yeah.
Thanks.
Any others? Okay, so yeah, let's thank Giuseppe again for the nice talk.
Thank you.